Our accumulator container is separated into two sections. One side, the module side, holds our modules as well as our battery management system. The other side, the high voltage enclosure, holds our AIRs as well as all of our safety circuitry. With the enclosure lids on, you can see that the high voltage was energized, as well as the high voltage warning stickers are visible from any angle. Within our high voltage enclosure, we have our lights board, our relay controller, as well as our DC-DC converter.
This board uses HV and LV in it. We use this for our T-cell and our voltage indicators. The optocoupler U1 is used to isolate the high voltage from the low voltage. The gap that we have in between the two is 4 millimeters as specified in the rules. As you can see, I'm measuring this gap with the calipers, and I'm getting 4.03 millimeters. This board also has conformal coating on it, as you can see while using this UV light. This is the relay control board. It controls the airs, the pre-charge relay, and the discharge relay. This board contains HV and LV and is separated by a clearly defined 4 millimeter band, as you can see with these two lines. And using calipers, I can measure and see that it is 4 millimeters. And you can also see that the board contains conformal coating, as shining a UV light shows the glow. This is our DC-DC controller. It also has HV and LV on the same board. We can see the separation is 4 millimeters, and with a UV light, you can also see that it is conformal coated.
Moving on to our HV path. As you can see, we typically use distorted thread nuts to provide positive locking within the path. Here, you can see a picture of our positive AIR with distorted thread nuts used to provide positive locking. Distorted thread nuts are also used to provide positive locking connections to our negative AIR. They are also used to provide positive locking connections for our main fuse. For OEM parts with blind holes, we use bolts with nylon patches to provide positive locking. This is an example of a bolt with a nylon patch used in our high voltage disconnect. Nylon patch bolts are also used for our main HV connector. This is a picture of our high voltage enclosure during assembly, which shows the high current path in orange wire. Clearly you can see there is no soldering within this high current path. Instead, only bolted connections between components. Here you can see one of our battery modules in the process of assembly. Separation of the cell stacks and the poles from the aluminum walls of the enclosure is achieved by our polycarbonate sheets, which separate the cell terminals from the walls of the enclosure. In addition, the walls of the module made from Ultem 1010 act to separate the poles of the battery module from the aluminum walls of the enclosure. Our high current path contains a 125 amp fuse, which is located in our high voltage enclosure. It's shown right here. In addition, we have two AIRs located in our high voltage enclosure. Our negative AIR is shown here, and then our positive AIR is shown here. Both AIRs, as well as the fuse, are protected from the aluminum wall of the accumulator enclosure by a piece of polycarbonate, which I'm tapping on here, that separates the entire back of the high voltage enclosure from the aluminum wall of the container. Just to show that the polycarbonate spans the entire back wall of the enclosure. Tapping on it again here. The only two tractive system wires that leave the accumulator enclosure are these two orange high voltage wires, shown here as well as here, which exit the container through this connector, shown up top. These two tractive system wires are both connected to AIRs. This one is connected to our positive AIR, shown here, and this other one is connected to our negative AIR, which is shown here. There are two branch wires coming off of each AIR. Both are fused within 150 millimeters of the source, which you can tell by inspection. For example, one fuse is shown here, another is shown here. Clearly both are within 150 millimeters of the source. Moving on to our negative AIR, you will notice the same thing. So it's a bit more difficult to see. We can see our negative AIR here. One fuse is here, and the other fuse is shown back here. Again, both are within 150 millimeters of our negative AIR. From each AIR, one fused branch leads to a fuse board that is less than 150 millimeters from that AIR. This fuse board contains various 1 amp and 2 amp fuses for other components that require HV power, while the wire that leads to that fuse board from the AIR contains a 5 amp fuse. This image of our high voltage enclosure under construction shows the location of the fuse boards highlighted in red. By inspection, the fuse boards are quite close to the inverter side terminals of both AIRs and are within 150 millimeters as required by rules. There are maintenance plugs, which provide series connections between the individual modules within our accumulator container. They consist of a bus bar, which you can see here, which is enclosed by some insulation made up of Altum 1010, as well as these two spring-loaded pins, which are also made up of Altum 1010. Of course, our maintenance plugs can be removed without the use of tools because they use spring-loaded pins. Simply press down, give the pins a half turn, quarter turn, and they can now be removed. In addition, of course, our maintenance plugs cannot be incorrectly installed. As you can see, this connection between the negative pole of this module and the positive pole of this module should be avoided. To do this, we structure the internal wall of our accumulator container with this raised surface such that it prevents the incorrect installation of our maintenance plugs. You can see that it is impossible to make contact with both poles at the same time. These raised portions occur whenever we want to prevent a maintenance plug connection. They also occur in the back where we do want to prevent a maintenance plug connection. And they do not exist where a maintenance plug connection should be allowed.
Like a Ziploc bag with 30 sticks.
We also have an indicator light, which is attached to the accumulator enclosure as shown here. The indicator light is connected to the lights board, which takes high voltage input after both AIRs. This indicator turns on whenever there's voltages greater than 60 volts present outside the enclosure, and because it only takes input from the lights board, is able to function when the accumulator is removed from the vehicle. Again, we have one tractive system connector leaving our accumulator enclosure. This is shown here, this cap. This connector, of course, has an interlock, which is shown on the underside. You can see these two wires leaving the header. In addition, we also use this connector for charging, so this satisfies requirement for a charging connector to have an interlock as well.
This is our charging system. This is the connector that attaches to our accumulator for the tractive or high voltage connection for charging. That is a low voltage connection to activate shutdown circuit. It connects to this box, which has our charging PDB, our charging control unit, which is just an Arduino, and then the shutdown circuit for our charging system. This attaches to these leads, which have two 600 volt DC/AC, 10 amp rated fuses put in line for both the positive and negative side of the high voltage, which connects to our off-the-shelf charger.
In addition, though it wasn't highlighted in the video, we do have two banana jacks coming from our charging enclosure, which connect to our TSMPs as specified in the rules. In addition, though we do not own an energy meter, we will be given one at competition. This will be placed within our high voltage enclosure directly after our negative AIR. Shown here is a mount that we've designed in order to attach the energy meter.